build one in. How many carbons? 4. 4 carbon. So at the first carbon you have an alkene, right? So over here, your first carbon should have an alkene. First carbon should have an alkene. Yes? Need to go through or not?
No, that's fine.
Okay, you all check your answer. There are certain things I want you all to double check. First, 1A and 1B, do you need me to go through? Double check carefully. Huh? Turn can. If you turn means that 1, 2, 3, 4, 5. Meaning you count the number 2 from the back, is it? That means you count number 2 from the front. 1, 2. So from here, can. 1, 2, 3. So like this also can. Is it okay? So 1A and 1B, no problem, everybody? 1A, 1B, no problem? No. But I need you to take a look at transhexene. For transhexene, I want everybody to be very clear. Your line, right, should be connected to a carbon. Because when I mark your intro to organic, I notice some of you do something like this. You draw like this, right? Then you write. Is this correct? No. I think some of your work is like that. Please check. This one is obviously cannot. Because it's not connected to the carbon. And when you're drawing trans and cis isomer, what do you take note of about the shape? Must be trigonal planar, okay? You definitely need to show this shape. Okay, show this shape and make sure that it is the same group on opposite side of the double bond. It's trans, okay? Then for cis, everybody take note of this part over here. It is CH2, CH2Br. I suspect some of you will write CH2Br, CH2. This is wrong. Huh? Do you all write like this? Yes. Okay. So based on this, check this one. You have Hep 3 in, right? So 1, 2, 3, 4, 5, 6, 7. Agreed? Carbon 3, I have an alkene. So 1, 2, 3, alkene here. So over here will be a H and cis 1 bromo. So 1 bromo, that means this is a Br. Do you agree? Can. So I try to transform into the normal one. So let's see how we do it together. Over here, this double bond, I have a H. Then over here, can you please check this part? This part, right? Okay, I link it to a carbon. Can you see after this carbon 3, the next one is CH2 already? So I need to write CH2 first. Everybody following? Then after I move again, then it is CH2Br. CH2Br. So I have to write in this manner. Is it okay? Rather than this. Can? The numbering. Then of course the other part is very straightforward. You just have CH2, CH2, CH3. This part, is it okay? Yes, clear already, right? The joining. So again, you need to show the trigonal planar shape. Can? Okay, so we continue from here. Question 2. Okay, question 2 says that there are 3 isomers of C4H8. Which 2 isomers exist as a pair of cis trans? Good. A and B. So you just check. For A, is it cis or trans? Cis, correct. B must be trans. Good. So based on this, you have A and B. And they say draw the displayed formula when A is reacted with bromine in CCl4. Firstly, right, if you have double bond, okay, let's do a quick recap. Alkanes undergo free substitution. Correct. For alkene, very good. Electrophilic addition, right? So when we do addition, what will happen to the double bond? Break. You have a sigma and a pi bond. Which one will break? Pi. Good. Pi bond will break, right? So over here, when you draw your working, right, you erase the pi bond. Then after that, you have bromine. So it's Br, Br. Then you actually, what do? put Br. You add across the double bond, right? So that's why it's electrophilic addition, because you add to the double bond. Okay, so based on this, your answer should be this one. Did everybody get this? Yes, good. This one is okay. Then continue on. Ensure that your answer is displayed, because the question mentioned displayed. Okay, so reacted with aqueous bromine. Plus, if you have aqueous bromine, right, what else do you have in your solution? Aqueous means H2O, correct? H2O is present in what? Large amount or excess. Okay, so in this case, you take a look for B. For B, right, on this carbon, I have one hydrogen and one CH3. On the other carbon, I also have one CH3 and one H. So does it matter whether I add BrOH or OHBr? Does it matter? No. So actually, it doesn't matter. So based on this, you should get an answer like this. Br on the second carbon, OH on the next carbon. And ensure that your OH is being drawn out because it's displayed. Is it okay? So this one, right, do we label it as the major or minor product? Major, right? Major because of the OH. If I want to draw a minor product, then what should be the OH here changed to? Br. Good. So if you have a minor product, right, both will be Br. And this one you need to label as minor. But the question... So you move on. C is subjected to mild oxidation. Okay, when you see oxidation, right, of course we always see KMnO4. But how do you know whether it is mild or strong? How do you see whether it's cold? Correct. So if you see cold, right, definitely it is mild oxidation. If it is mild oxidation, what kind of product will you get? Diol. Correct. Diol. So you will get OHOH. Everybody got this? Yes, good. So this part, ensure you draw out the bonds because it is displayed. Yihui. Okay, please pay attention. Next part, am I going very fast? No. Still manageable? Yes. Okay. So next part, they say it is subjected to strong oxidation by hot KMnO4. So this sentence, take a look. This sentence, even though if they never tell you it is strong, what is the condition that tells you it is strong? Hot, correct. It's hot. It tells you that it must be strong. So if it is strong oxidation, right, instead of getting a diol, what will happen to your double bond? It will undergo what? Oxidative cleavage, correct. I need you to take note of this structure. What do you call this part of the structure? It is a what? This part is very important for your alkenes. Terminal? Terminal what? Terminal CC. Correct. Double bond. Terminal CC double bond. Okay, so everybody, when you do oxidative cleavage, half. Then your double bond, you just break into half. Then what do you do? Correct. Add an O. So based on this, right, you will get like this: C double bond O, CH3. Draw out all your bonds. What will happen to the terminal double bond? Become what? Okay, let's try to do it slowly. You break already, you put a double bond O, right? Then the H, what will happen to it? What will happen to the H? Further oxidized, you will get what? OH, correct. So every time you see a H there, you must change to a OH. So you will get this. Everybody okay? So after you get this, right, actually it will further oxidize to CO2 and H2O, correct. So that means every time you see this structure, this part will always give you CO2 and H2O. What's further oxidizing? Is it okay? Can? This part no problem? Okay, so we'll move on. They say it is possible to react the 3 isomers with hydrogen bromide to give products, and the products have some optical isomers. Draw structures of the pair of optical isomer. Okay? When you react with hydrogen bromide, remember we say in the tips lecture, we have HX. Okay? Hydrogen bromide is like HX, right? If you react with alkene, with what rule? Markovnikov rule. Correct. Is it okay, everybody? Can. Okay, what does Markovnikov rule say? The H must be added to the carbon where there is more. Yes, the rich get richer. So based on this, right, let's see. You have these 3 products. You have these 3 starting material. On this first carbon, there's only 1 hydrogen. On the second carbon, also only 1 hydrogen. So that means, does it matter where you add your H and Br? Does it matter? Doesn't matter. So you should get a product like this, right? H, CH3, and I'll just by chance just put it here. The other side just H, CH3, and the other one I put a Br. Everybody okay? Please check your answer. And then for B. For B again, it is just 1 hydrogen and 1 hydrogen. Will you get the same answer as this? You will get the same answer, right? If you try drawing out, you will have a H, CH3, H, C, H, CH3, and Br. Can everybody? Do you notice that for A and B, right, my product is exactly the same? Agree? Whereas for C, right, you just try. For C, where will you add the carbon? Where will you get a hydrogen to? The first or the second carbon? Where will you add your H to? The second carbon, correct? The second carbon has 2 hydrogen. Over here, you notice that there are 6 hydrogen here, CH3, CH3. But this is not directly attached to the carbon, so ignore them. We only want the hydrogen directly attached to the carbon. Is it okay? So this part you should get C, H, 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 and the Br should be on the other side. Okay, so you should get this. So based on all these 3 products, okay, since the first 2 are the same, I will just erase one of them. Which product is optically active? First or the second one? Sorry? The first, right? First, which carbon is chiral? 1, 2, 3 or 4? Which carbon is chiral? 3, correct. This one is chiral, so I have 1 different group, 2 different group, 3 different group, 4 different group. So over here, if you notice, this group is actually a CH2, CH3. So where would you prefer to place it? On top or below the wedge, okay? Either one. So based on this, right, you can actually get this structure. Did everybody manage to get this? Check your 4 different groups, okay? Ensure that your wedge is connected to a carbon. Your wedge is connected to a carbon. Everybody, yes?
When you know you must draw the product, when you know you must write out the step.
Okay. Okay, good question. Melissa is asking, because there are so many reactions, right? How do you know that you can just draw the product? How do you know you don't need to draw the arrow, the mechanism, is it? Okay, if they want you to draw the arrows and everything, right, they will ask for the mechanism. If they just ask you give the products, you can just draw the final one. Okay? This one, can I move on? Yes. So we move on to question 3. Okay. For question 3, right, let's do a quick recap. For ethene, right, it is hybridization. What type of hybridization will be present? sp2. Very good. For sp2, right, how many hybrid orbitals are there? How many? 3 or 2? 3, 3 sp2. And there is one unhybridized orbital. What is the identity? P, correct. There is one unhybridized p orbital. Do we need to draw around the carbon atom? No. And they only say one carbon atom. So you only just need to draw this. Just only need to draw this, 1, 2, 3. This is sp2, sp2, sp2. Do you need to draw the hydrogen atom? No, the question didn't ask you to draw. Then the next part, they say explain, sketch the pi bond. Everybody, sketch the pi bond, right? How many of you draw this part? How many of you drew this on your diagram? Okay, if you draw this on your diagram, right, you cannot just leave it like this. You have to draw the dotted line and the dotted line and with the pi. Is it okay, everybody? 10? This part okay. So I'll move on. The question asks you for explain why the pi bond is a localized pi bond. Anybody can explain why it's localized, meaning? Localized meaning what? Fixed. So you fix. Fix. And over here, when we talk about localized, okay, it is the 2 electrons. The 2 electrons can only move between the 2 carbon atoms. So it's meant by localized. In your benzene ring, right, how many carbon are there? Of course, 6, right? Remember, for each carbon atom, is sp2 or sp3? Correct, very good. This one need to know. Benzene ring carbon is always sp2. So on each carbon, there is how many p orbital that is unhybridized? 1. There's 1. Okay, like this, right? So based on this, right, benzene ring has how many pi electron? 1 p orbital inside only left 1 electron, right? So 6 pi, you have 6 pi electrons. So these 6 pi electrons, it is actually moving around the 6 carbon atom. So that's why it's delocalized. And that's why you draw a ring. Is it okay? Because it's like moving around the 6 carbon atom. Is it okay? So this part is delocalized 6 pi electrons because it is moving around the ring on the 6 carbon. Okay, next part, they say state the major and minor products. Okay, sit down first. Okay, when you say state the major and the minor, let's see. Class, if we have a HBr again, what's the rule? Markovnikov rule. Okay, again for Markovnikov rule, check your carbon atom. Which one has more hydrogen attached to it? The first or the second carbon? Second. Over here I have 1 hydrogen atom. Take note, the hydrogen atom must be directly attached to this carbon. These 3 not counted because it is attached to a carbon. This 3 hydrogen is attached to a carbon, then attached to a carbon. You must have the hydrogen directly attached to the double bond carbon. So that means your major product, the H should be on this side, right? And your Br is on the other side, agree? For your minor product, you just need to swap, correct? So everybody, do you manage to get these 2 products? Check answer. This part is Br, Br. Is it okay? And then please label major and minor. This part is important for mid-course. Everybody needs to know how to apply Markovnikov rule. Okay, take note, Markovnikov rule. How do you apply? The H add to the side that has already more H. Is it okay? Can? Yep. And we can move on from here. Question 4. Okay, let's take a look at this part. This part, you have 3 structures, okay? 3 products formed in equimolar amounts. Equimolar means what? 1 is to 1 is to 1. 3 of it, 1 is to 1 is to 1. Okay? And over here, remember for double bond, when we cut, right, what do we do to the double bond? Add a O. So now if we have a double bond O, if we want to get back to the alkene, we just take away the O and combine, correct? So based on this, right, you notice that the ring structure is symmetrical, right? Both sides are the same. So now I have 2 different alkenes. What can you do to combine them? You can take this and put on this side, agree? Correct or not? Then the other one, this one, you can just put on the other side. Do you agree? Everybody okay? Can so this part, if you want to combine them, you just remove the oxygen and put them together. So finally, your product should look like this. Everybody got this? Huh? Okay, I think this part, right, some of you will get the CH2 here, right? It's because you draw exactly from the question. Over here, my answer is showing you the skeletal structure. You should get this. Everybody clear of the understanding? Just piece the double bond, make them face each other. Then you combine them. Is it good? I know, I need to finish. Okay, can? Continue. Okay, let's move on. Okay, then move on. Okay, next one. Continue from here. Okay, question 5 already. Moving on. Yeah, question 5, right? They say describe a simple chemical test to distinguish the following pairs of compounds. State your observation. Okay, firstly, right, we have AIM. AIM means what? Functional group. Alkane. And it's cyclo and it's hexane 6 carbon, so we should have like this. Okay, cyclohexene. Alkene. Cyclo means ring. Hexene means 6 carbon, so you got this, right? So based on this, right, everybody, if you are distinguishing between alkenes and non-alkenes, once you see an alkene, you can use 3 tests. What are they? Bromination and hydrogenation. But hydrogenation is at H, right? You cannot see any color change, so cannot. Simple chemical test must enable you to see color change. So yes, correct, KMnO4. So for bromine, right, you also have 2 different ones, right? One is aqueous, one is liquid. So that means your answer, right, you have to mention aqueous. And if it is aqueous, right, the color is orange. Because aqueous means there's water, the color appears to be lighter. Okay? Then in the dark, what is the purpose? Prevent what? Yes, very good. Prevent free radical substitution. And over here, right, they say orange bromine remains because it doesn't react with the alkane, right? Agree? If it doesn't react, can I say that there is no reaction? Can I say that there is no color change? Actually cannot, because the question asks for observation. So if you say no color change, you also don't know what is no color change. You need to say the orange remains. Is it okay? Huh? No, you also cannot say will not affect the color, but what is the color? You need to say the orange color stays. Is it okay? Next part, liquid bromine. Liquid bromine will, because it's more concentrated, so the color is darker, reddish brown. The reddish brown for alkene, because it reacts with alkene, right, use up the bromine. That's why the bromine will decolorize. But it doesn't react with alkane, so the reddish brown remains. And always remember is room temperature in the dark is to prevent free radical substitution. This part, everybody is okay? Can. I'll move on, okay, to the KMnO4. For KMnO4, take note of the details. KMnO4 must be with dilute H2SO4. If you just put acidified KMnO4, it is also not taken to be correct, because again acidified means you can use HCl or you can use nitric acid, but both also cannot. Okay? Can only only H2SO4 can be the acid. Okay, and also add to the compound separately and heat. Please do not say heat with reflux, because reflux requires a very complex setup. Okay, so we can just say heat. And similarly, the decolorization is of purple. For cyclohexane, no reaction, so purple solution remains. Everybody okay? I will move on. Is it okay? Next part. If you look at these two alkenes, both are alkenes, so can you still use bromine liquid or bromine aqueous? No, cannot, because both will decolorize, so no difference. So based on this, can you use KMnO4?
No.
Why not?
Yes.
Yes, right? Yes. What is so special about this alkene? It is what type of alkene? Correct. Terminal. Okay, so based on this, if you cut, okay, what product will you get? You will get this, right? Double bond O, and over here you will get double bond O. Yeah. Then this part, if you have a H, what will you change it to? OH. Okay, if you have a H, you change it to OH. Then ultimately this part will become what? Correct, CO2 plus H2O. Okay, and then for the other compound, it will also break. And when you break, you will get the double bond O, and you will get C, double bond O, and you will have a CH3. Plus over here, you see a H, right? Again, what does it become? OH. You get an OH. Correct? So based on this, if you see that there is CO2 being observed, your observation is you will see bubbles, right? So you talk about effervescence. So based on this, you notice that the KMnO4 is still with dilute H2SO4 and heat. Do not say heat with reflux. Okay? And over here, you will have decolorization of purple KMnO4. And it is for both situations. Okay, for both you will decolorize because both will undergo oxidative cleavage. Okay, but only for the terminal double bond. Always remember when you see terminal double bond, you will have to say effervescence observed. What is the identity of the effervescence? Correct. This gas is CO2. And please do not say lime water. Use calcium hydroxide. I mean, although they are the same, but lime water is a commercial name. So the learning point for this question is if it is two alkenes, right, straight away zoom in on whether it's a terminal alkene or not. Okay, terminal alkene will give you CO2 gas. Can I move on from here? Yes. Can I? Okay, next part, question 6. Okay, question 6, right, is also quite similar, quite simple. You have C7H14. When you have addition of hot acidified, first thing when you have hot, right, is it a strong oxidation or weak? Strong. Very good. You have strong oxidation. Okay, you have strong oxidation and you have propanone being formed. Because if you have propanone, right, ONE means what? Ketone, correct? And you have methyl propanoic acid. So firstly, let's see what's the structure of propanone. Propanone, how many carbon? 3. So over here, let's see, you have 3 carbon. 1, 2, 3. And ketone must be on which carbon? First, second, or third? First, like this. If it's on first carbon, over here will be what? H, right? But remember, we say ketone must be 3 carbon in a row. Remember? So ketone is definitely in the center. It must be in between 2 other carbon. Okay, so this is my propanone. Okay, then for 2-methyl propanoic acid. Propanoic acid again has 3 carbon. So 1, 2, 3. Agree? And 2-methyl. So at the center is definitely carbon 2. But propanoic acid, right? So on one of the carbon, I didn't add any carbon. I just put on a double bond OH. So over here, carboxylic acid will take 3 or 1. Which number? Can you please take down? Take carbon 3 or 1 for carboxylic acid. 1, 2, 3 or 1, 2, 3. Top or the bottom? Top. Very good. Because oxidation functional group should always take. Correct. So over here, your CH3 must be number 2. So you get CH3 and H. Everybody okay? So after that, they say you must find the original structure of Y. So since you know that double bond, right, you cut already, you put in the oxygen. So now you already have the C double bond O, right? What do you make them do? Huh? Arrange them such that they face each other, correct? Form double bond. So based on this, you just draw properly, make them face each other. This part is CH3, CH3. Okay, make them face each other. CH3, CH3, and H. Okay, class, this part you see that there's an OH, right? So before oxidation definitely is what? H, right? Very good. It must be a H. Take note, because always we know that you cut must add a OH. So now you put it back, you must remove the H. Is it okay? So now you put them back together, remove the O, then you just connect. So this is your alkene. Is it okay? Can? Just remove the 2 oxygen, connect. Can? This one is okay, right? Everybody, does this exhibit geometric isomerism? Geometric? Yes or no? Yes or no? Have cistrons? This molecule have cistrons? Why no? Cannot say same. This carbon has 2 same group on what? On each carbon atom of what? CC double bond, correct. This one everybody take note, you need to know how to explain. There are 2 same group, so cannot exhibit cistrons. Is it okay? So I move on. Question 6. Okay, left with 3 questions, very fast only. Huh? Okay, class, I will move on to question 8. Okay, let's hang on. This mechanism, you need to know for mid-course. Describe the mechanism of the reaction between 2-methyl propene and HCl. Let's see. 2-methyl propene, you try drawing out. Propene means how many carbon? 3. Correct, 3. 1, 2, 3. And propene, Propene is just like this, right? 2-methyl. So 2-methyl means on the second carbon you have a CH3. And over here is H and H. Then you have HCl. Class, what rule comes into play? Markovnikov. This part I must cut away. Okay? HCl. You have HCl, you think of Markovnikov rule. Okay, so over here, you will add your H to which carbon? The first or the second? First, correct. If you add your H to the first carbon, let's take a look. Over here, the question says describe. Take note, describe the mechanism. You need the name, electrophilic addition. Okay, so over here, the double bond, okay, it will start from the double bond. Electron rich to what? Electron poor. Take note over here, you need your delta plus and delta minus. Okay, H is delta plus, and then your bond here will break and give the 2 electrons to Cl. No, you don't need to draw the 2 electrons here, it's okay. No, your electrons later you have to draw at the back. Over here, ensure that you label slow. Everybody, why is it slow? Because you are actually breaking what type of bonds? Between atom is what type of bond? Correct, covalent bond. Okay, it's slow because you are actually breaking covalent bond, which are very strong, so you need a bit of time to break it. So over here, everybody, look closely at the magic. You have 2 carbon, you have 2 hydrogen here, and then you add another one more add to the same carbon. Markovnikov rule. So if you add it to the first carbon, that means your plus sign will be on the other carbon. Agree? And this one is a carbocation because it is a cation because positively charged. Okay, and it is a Cl minus with a lone pair. Cl minus with a lone pair. Is it okay? Can. So this carbocation, we know that it is the intermediate. Okay, you need to know this about the intermediate. For this carbon, initially is sp2. This carbon originally also sp2. What about this carbon from sp2 become? Correct, sp3. So this carbon now is sp3. This carbon remains as sp2. Because 3 sigma bonds. 3 sigma bonds. Okay, after that, make sure you have your lone pair. Okay, your lone pair on the Cl minus being transferred to the carbocation with a plus sign. Okay, and then over here, it will be fast. Why is it fast? Why is it fast? You have attract, correct. Positive attract negative ion, attraction, so very fast. And based on this, you get your major product. Okay? Can everybody? If you have a minor product, that means your H and the Cl just swap, correct. Can everybody? Yes. So this is electrophilic addition. Can we move on to question 7? This is question 8, 7 then 9. Okay, good question. Rebecca asked whether do you need to write step 1, formation of carbocation. Step 2, actually not required to draw, but for free radical substitution, need. Remember, free radical substitution definitely need. And the naming? Yeah. Yes. Okay. Let's go.
Last question.
Question 7. Can I move to that?
Yeah.
Yes, Okay. Okay, question 7. Okay, I need you to pay attention to this one. Question 7 occurs in two isomer. Yes, two isomer form. Hexene. How many carbon?
6.
6. 1, 2, 3, 4, 5, 6. Hex 3 in. So at the third carbon, draw a
Double bond.
yes. Okay, so based on this, you have a H and a H. And cyclohexene, like this, right? Ring. Correct. So over here they say isomeric. What type of isomer?
Cis trans.
Yes, good. This one must be cis trans. Okay, cis trans. Over here they say draw displayed formula to explain why such isomerism is not possible with cyclohexene. Yes, ring this restriction.
Yeah, 70.
Everybody managed to get this or not?
MR higher
MR higher? Because this one, obviously this is MR higher, right? So if it is trans means opposite. Alternatively, you can take a look at the H. Also opposite. Is it okay? For cis, of course, same side. Everybody take note, this is displayed formula, so you need to draw out all the structures. The catalyst. 先春加油 Okay? Can? Everybody? Hey, catalyst, Okay, can we move on to 7B already? Okay, we are still not copy this part yet. Cyclohexene cannot exist in trans. It can only exist in cis. Cis, right? This part same side, only cis. Is it okay?
Not cis, then trans.
Because over here there's a ring here, right? You can imagine like a chain to the table. If you want to flip this part over, this part will restrict you from flipping it to the other side, right? So ring strain. Is it okay? Ring strain. So I move on to 7B. Okay, 7B. Huh? Need to draw this, is it? This one you don't need to draw, but you need to show this answer. Okay? It can only exist in a cis configuration. Can? Okay? Okay, B. Describe the mechanism. Everybody, what type of mechanism is it? Yes. State the condition, hex 3 in and liquid bromine. What is the condition? You need in the what? In the dark. In the dark, and what's the temperature? Room. Correct. Okay. So in this case, take note again. Over here you have BR because bromine. Take note that it is Br delta plus and delta minus. Okay, and take note it is electron rich. Electron rich to electron poor. So your arrow goes from electron rich to poor, correct? And your bond will actually break. 2 electrons give to bromine, so bromine will take the lone pair. Is it okay? Remember to put the minus. Over here, does it matter which side you put the Br on? No, right? Because it's symmetrical. So I will just put it on the first carbon. If I put it on the first carbon, the other carbon will get a plus, correct? And you call this a carbocation. This is an intermediate, right? Intermediate must always be used up in the second step. So you produce the intermediate is a slow step. Then you use it up is a fast step because it's plus and minus opposite attract. And it's always from lone pair, remember to draw the lone pair, to the positive charge, and you get BR. Everybody okay? Yes, need to label carbocation. Okay, label carbocation and also label the delta plus and delta minus. Can? This one no problem? Okay, continue. Next part, right, they mention draw the structures of all the possible products when a small amount of aqueous NaCl is added to the reaction. When you have aqueous, what do you have? Water. Na plus and Cl minus. So based on this, right, can you look at the mechanism again? Now I'm going to erase everything on the mechanism. Okay, firstly, class, over here, this carbocation, right? You have this carbocation over here. The next step is actually Br minus come and attack it with the lone pair. If you have Cl minus, it will also attack this. Do you agree?
Yes.
What if you have water? Lone pair will also attack. Na plus? Na plus also? Attack? No. Okay. Over here, please take note, your water is H2O. So you cannot write OH minus. If you write OH minus attack, it is wrong. OH minus can only come in if you have things like NaOH. Okay, like base. Base, then you can use OH minus. If it is water, aqueous, then you can only use water. Is it okay? So based on this, right, your product is simply how? That means this product, how will you modify it to get the other product? Change which bromine? The first one or the second one? Second one, change it to Cl. If not, change it to, but it cannot be H2O, it must be OH. Everybody understand this part? Yes? Can So over here, do you notice all your product have the Br over here?
Yeah.
Why is that the case? It's always Br here because all your nucleophile attack the same carbocation, right? Your carbocation already has the Br here, so this one definitely must be Br. The rest you just change Br, Cl, OH. Which one is the most major? Which one is the most major product? The one with what? OH, correct. This is the major. Then the other two must be minor. Everybody okay?
Yeah.
I can let you take a look at the answer, okay? You just change B, OH, Cl. Can everybody? Yes. Move on. We are moving on fast. Part D already. Explain. Okay. Explain why the reaction of either isomer of hextrine with hydrogen bromide gives the same equimolar 1,1 mixture. First thing, again you are reacting with hydrogen bromide, HX. So what would you think of? Markovnikov rule. Markovnikov rule. So 1, 2, 3, 4, 5, 6. Okay, class. Over here, hextrine is like this. Same number of hydrogen on each atom. Does it matter whether I add HBr or BRS? No, right? So if you don't mind, right, I just add it to this carbon and Br. So which is the chiral center? Definitely the
Fourth one.
this one, chiral center, right?
Yeah.
So I have 1 different group, 2 different group, 3 different group, and 4. Everybody okay?
Yeah.
So over here, this part I will get CH2, CH3. This part I will get CH2, CH2, CH3. Can you see CH2, CH2, CH3? CH2, CH3. Based on this, I place them on the dotted line with the 2 mirror images.
Yeah.
Okay, so over here, can you all just take down this same equimolar mixture of the 2 isomers? Isomers here refers to optical isomer. Okay, it must be optical isomer, no other possible one already. It cannot be geometric because no double bond. Okay, so based on this, right, take note, your answer should be like this. Ensure that your CH2, CH2, CH3, right, goes from left to right. And it must be this bond attached to this carbon. Not the whole chain, just right in the middle anywhere. Is it okay, everybody? If you want to place this big group, because you always say big group, place on the vertical part, either top or bottom. But if you want to place it at the side, right, on the reflection, you must write CH2 in this manner. Okay? Is there anything wrong with the wedge and the thing? Correct. It should be like this. Dot, 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 dot. Then like this. Dot, 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 dot. Huh? Yes, anything? Okay. Continue. The electrophilic addition. Chiral center connected to 4 different groups. Hence, there are equal proportions of the optical isomer exist as a racemic mixture. Okay. So, class, right? This part, racemic mixture, right? Okay. Racemic mixture, very simple. You can just simply think of it in your intro to organic, page 33 of your lecture notes. Racemic mixture. Okay? Okay, class, for this racemic mixture, right? Okay, do you want me to, okay, before I explain this, do you want me to explain question 9 or upload to LMS? Upload. Okay, so better go there and see. But in the meantime, let me finish this. Is that okay? Okay. This racemic mixture thing, right? Okay, check this racemic mixture, right? Remember that time we say one of these optical isomer. This optical isomer, you remember we say that it can rotate plane polarized light. Remember? One rotate to the left, the other one rotate to the right, right? So over here, racemic mixture just means that there is in a container, right? 50% of the molecules is this. The other 50% is this. So this is a racemic mixture. That's just what it means. So what is the significance? The significance is that this molecule, right, rotates the plane polarized light to the left. This one rotates to the right. So when the light passes through, one is trying to rotate to the left, one is trying to rotate to the right. So when the light passes through, where will it rotate? Will it rotate anywhere? No, right? It will pass straight through, right? Okay, so when it passes straight through, it just means that it cannot rotate plane polarized light, right? If it cannot rotate, is the whole mixture optically active? No, okay? So this is the main thing. Racemic mixture, okay, just take down this part, contains 50% is to 50% of each isomer. Okay, so the rotating, so the optical activity of each isomer cancel out that of the other. Okay, cancel out already, right? That means there is no optical activity. There is no optical activity for the racemic mixture. Okay, can? So over here, right, one of these is optically active. The other one is also optically active, but put together 50-50, overall not optically active. Because it cannot rotate plane polarized light. Cannot rotate plane polarized light. Is it okay, everybody? Yes.